G'day there, you're watching the Aussie BIM Guru. Today I've got a quick video just covering how you might be able to estimate some formwork based on a structural model using Dynamo. So I know this is a little bit of an off-topic sort of topic for me, I guess, but I had a request that I thought would be interesting to explore from a follower on the channel who watched the 5D estimation video and queried if it would be possible. And it sort of is. I'm going to show you a workflow using Dynamo. It's quite high level, so I do have to say I'm not a structural engineer or a formwork expert. There probably are some more details you might need to add to this workflow to make it more accurate and true and correct. But the general method is that we're going to be trying to isolate the combined result of structure and all the faces that aren't pointing directly up or upwards. So in this case, any face that's side facing or down facing will be collected and measured as a set to generate a very high level estimate of how much formwork you might need to support a setting in situ structure like this. But there will be some bugs and geometry issues sometimes, especially if your model is large, very complicated, and has awkward junctions. For example, I do have a structural model I'm developing, and I did test it with this workflow, and there were some issues with joining solids together using a union function. From what I understand, there are some certain limits that a union will face in Dynamo. So alternatively, if you have a very complex model, maybe think about exploring Rhino inside as an alternative. But today I'm going to show you it in Dynamo using the Autodesk Structural Sample Project. So I'm using Revit 2020.2.2 and Dynamo 2.3.0, and you shouldn't need any custom nodes in order to run this script. So without further ado, let's just jump straight in. So I'm using the Structural Sample Project by Autodesk. In this case, we're going to be isolating columns, beams, floors that don't belong on level 0, and also the walls for the cores as well. So we're going to begin by collecting all these elements in Dynamo. I'm just going to begin with a category by name. Oh, okay, I need to be in the actual noding view. Sorry, I think I've got a yeah, there we go. That was a good start. Okay, so category by name. And we're going to start with, where's my notes? There we go. We're going to start with the category of floors. And in this case, we're going to need to collect all the floors that aren't on the ground, because these would need to be propped up with some sort of formwork when you build them. In this case, we're going to use the element.get parameter value by name. And we're going to be collecting the parameter value of level. So we're going to just make a code block for level with the string level. This should return, I'm just going to go to automatic mode actually, so my script keeps running. I've actually forgot to put one node there, so we need to do the all elements of category as well. So once we have the category, we get the elements, then we get the parameter, my bad. Now we should have all of our floors, and we're interrogating each of their levels, which is returned as an element, so we can actually interrogate data out of this level now. So in this case, we're going to be querying the elevation of that level above ground level. And I know in this project, the ground level sits at 0. So in this case, we can identify the floor or the floors that sit at 0. In this case, I'm going to say does level, I'll just say L, is it greater than 0? And we're going to form a mask of true and false statements. And we can see now we've detected when the floor isn't higher than that. And we're going to use a filter by Boolean mask in order to identify that floor to Dynamo. After this, we're going to use our in list, in this case, to take the floors that are above level 0, and we're going to obtain their solids. So we're going to use element.solids. And this will just obtain all the solid geometry in those floors. Now if I zoom to my model scale, we'll see we've obtained all the floors above that level. We're now going to need to collect our walls. Now this is a much easier step because all the walls in this project are in situ concrete, but you could filter them down if you had some other types of walls that didn't require formwork. But I'm just going to copy these over here, and instead we're just looking for the category of walls. So this is a much easier step obviously, because we're just going to obtain the solid geometry, and now we have our walls as well ready to be collected. We're also going to copy the front of this workflow here. And we're going to be taking those nodes, and instead of interrogating floors, now we're going to interrogate structural floors. Structural framing, sorry. So we're going to collect all elements of category structural framing. Instead, we're going to be interrogating the property of structural material. We're going to find all the columns whose structural material is concrete. So we should get a list of materials, and we're going to get the name of those materials using an element.name node. And in this case, we should be able to collect the names of those materials. Now, most of these are going to be concrete, but some of them are metal, steel. So we're going to filter these out. We're going to use a string contains node. And we could either filter the steel ones out or the concrete ones in. In this case, we're just going to search for the strings, or look for a contains node, and we'll get the string contains node. And we're just going to find all the materials that contain concrete. And we're going to ignore case. So we're going to say true for ignore case, because maybe it's lowercase, maybe it's uppercase. And then we'll get a list of true false statements for all the materials that contain the word concrete. We're then going to get a Boolean mask, and we're going to filter each structural framing by its structural material. And we should find now that our out list will be all of our steel, and our in list is all of our concrete. I'm going to take this whole piece of the code, copy it, and we're just going to do the exact same thing, but instead for structural columns, because they also have a structural material property, and we can filter out the columns similarly. So we'll end up with all the concrete, and then our out list is all the steel. And we're going to also collect the solids from the in list of those. Now at the moment, we could assess the face geometry of these elements, but the problem is that some of these surfaces will overlap. So what we need to do is combine these into a joined set of geometry instead. So you notice sometimes Dynamo sort of jumps behind when it's using a lot of geometry. It tries to hide itself. Very frustrating behavior. I don't know if that's Dynamo or that's Windows trying to protect the computer from using too much memory. I think it's a Windows behavior, but yeah, it's pretty annoying. Anyway, we have our beams, we have our columns, we have our walls, and we have our floors. So now what we can do is I might just turn off the preview for them, because we're going to combine these in a big list, because we want to merge these all together. So I'm going to use a list create. I'm going to make 4 items, and I'm going to collect each of those sets of solids. Now they're all together in one list, but at this point they're sitting at lots of different levels in the list, so it would be quite hard to join them together. What we're going to do is turn off the preview. We're going to flatten this list just to remove all the levels and place all the items at the same level. And then we're going to call on a union function. So we're going to use a solid by union. And we're going to union all those solids into one solid. Now this is the point where the script will sometimes cause errors if you have a very complex model. Union is sometimes something that won't work in all scenarios. So you might see some errors at this point. In that case, you may need to either look at where the error might be occurring in your geometry, or explore more heavy computational programs such as Rhino and Grasshopper. Anyway, at this point, you can see the union has worked. There's still some elements that are sort of rogue, such as these columns that are actually piles sitting below the columns, so we're going to manage those out. So what we're going to do now is we're going to explode our solid to get all the faces that belong to this. So we're going to explode this geometry. Now this might take a little while because we're going to get quite a few faces from this outcome. But none of these faces should be overlapping because we've taken this from a union solid in this case. So we just have a whole bunch of surfaces. And in this case, we're going to need to actually be interpreting these elements together. So we're going to be assessing the normal, or which way the face is facing, because we know that if a face is pointing up, we're not going to be using Formwork to set this face. We're going to be forming the sides and the base of the concrete as it sets. So at this point, we're going to be calling on some surface-based nodes. I'm going to use surface point at parameter. And of each of these surfaces, we're going to assess it at a UV of 0.5, or halfway across the face in both directions. And we can see that we now generate a point at the middle of each face. We can start to see a few rogue elements appearing in here as well. Now these are actually the center of the floors, I believe. So they're probably not rogue because the floor is actually a pretty big element. But we can see that we're getting the center of a lot of faces now, lots of points that represent those, which is great. And what we can do with these is we can get a surface.normal at point. We could also do a normal at parameter as well, but I'm going to use the point to do a few other things later on, essentially checking what height the surface occurs at. So we're going to do normal at point. We're going to take a surface, and at its respective point, we're going to assess its normal. And we should get a vector returned, so an x, y, z component, indicating the direction the vector is facing. Now at this point, we're going to want to filter out any faces that are pointing to any degree upwards. So at this point, if the z value of the vector is greater than 0, we know that we don't want to keep this face in our final assessment. So at this point, we're going to use the vector.z node to assess the z component of each of those vectors that represent the normal's face. Some of these vectors are going to be very small decimal places. So what we have to do now is just round these off. I'm going to get the round node, and I'm going to use the math round node with the digits specified. We're going to round it with 2 digits. And in this case, most of those figures that had very small decimals will typically be corrected to 0 or 1. So now we should see that we're looking at much more logical vectors. Most of them are actually pointing directly up or down. Actually, they all are. They're either pointing sideways with a vector value of 0, -1 pointing straight down, or 1 pointing straight up. But if you had faces on slight angles, you'd get some numbers that aren't quite 1 or -1. And we're just going to check if the vector is equal. In this case, we're going to say, actually, is the vector greater than 0? So is the z value of the vector greater than 0? Because if it is, it must be pointing up. So we have the first condition we're checking for. The next condition we're going to check for is that surface at 0 or below 0? And this is how we're going to manage out those columns that are being piles, and also the bottom of the column sitting at the ground, because we're not going to form those elements because they're in the ground foundation setup. So what we're going to do now is get a point.z node, and we're going to assess the z component of the center of the face. And we know now that those pile faces are going to be lower than the ground, and the bottom of the columns are going to be sitting at 0 as a point z. So we're going to say, is z less than 1? And if it is, this will be true. So this is going to let us essentially filter out some elements. Now in this case, we're checking if the vector is pointing up or in some direction of up, and is it less than 1? So we have 2 conditions. So what we're going to do is combine this list of outcomes. I might just move this model off just a little bit for now. So I'm going to create a list of those 2 lists. And we're going to need to transpose this list so that the outcomes form pairs, because at the moment we just have 2 really long lists of those 2 conditions. But if I transpose this list, then we're going to combine the outcomes on a face-by-face basis. So now we can see that we can check when it's pointing up or when it's lower than 0. And in this case, we're going to be checking how many occurrences of false are in the list, because we know that the only things we care about are the faces that don't meet either of those criteria, because they're the ones that are going to be less than 0 in the z direction, and they're also going to be higher than the ground level. So we're going to count false. Now you could do count false or count true. And what we're counting is each list. So we're going to have to work at level 2, because our sublists occur at level 2. And now for each list, we'll get a number that indicates the number of values of false that occur in that list. And we obviously only care about the faces that have both of those conditions false. So we're going to say boolean equals 2. And we're going to check which of those lists have both outcomes as false. We're then going to take a filter by boolean mask, and at this point we can filter all of our faces by that condition. So I'm just going to take this all the way back to my surface. So what I can actually do is probably move a lot of this down and out of the way, just to keep this a bit more simple. Excellent. And now we'll have 2 lists. We're going to have an in list and an out list. The in list is going to represent the surfaces that likely need formwork, and the out list is going to represent surfaces that likely do not need formwork. We can verify this by using a geometry color node, just so we can see that representation in a colored form. So we're going to turn off the preview for these surfaces, and also the exploded preview as well. And I'm going to take firstly my in list, and I'm going to make this blue. So I'm just going to get an ARGB, or color by ARGB node, or alpha, red, green, blue. We're going to do alpha of 255, red can be 255, and green can be 0, blue can be 0. So we're just making the color of red. And we'll apply this to these faces. Likewise, I'll get another color, and I'm going to make this color blue. So I'm just going to make the red component 0, and actually we'll make it green, 255 for green. And we're going to take our geometry color node and copy it, and we're going to take our out list, and then we're going to override this to be green. Now let's have a look at what we get. Well, there we go, we have our results. So we can see all the faces that likely need formwork are going to be in red. Notice that in this case, we can see that the bottom face of this wall is now green. Same with these columns. And we can also see in this case that some of these faces have been excluded. For example, all the faces that sit below the ground are excluded, and all the faces that sit on top of the slab have also been excluded. So we've successfully filtered out all those faces. And all we need to do with these now is just assess their area. So we can take an area node, and we're going to find the surfaces area. So from here, we're going to go back and take our in list, which is all the successful faces. We can verify that just by checking it and seeing what color. So see, that's our successful faces pointing down. I'm going to convert between units because currently the result will be in the native Dynamo unit, which is millimeters or square millimeters. So I'm going to convert using area from square millimeter to square meter. And then all I have to do is sum and do a math sum of all those values. And the result should be my total surface area that likely requires a formwork edge. So hopefully that's an interesting workflow that shows you how you can process geometry using things like explodes and surface normals in order to verify a condition based on the direction some faces face. It's a really handy workflow for a lot of other techniques when you're just trying to assess particular faces pointing in particular directions of elements. So hopefully you found that interesting, and you can find some application for it in other things you might need surfaces for. So thanks for watching today. The script will be on my GitHub as usual. If you've got any questions about the workflow, feel free to leave it down below. Like I said, you might run into some errors depending how complex the geometry of your model is. In which case I would direct you to the Rhino Inside series on my channel, which can typically handle geometry much more easily. But thanks for watching today. If you're not already following and subscribing, feel free to do so, and I look forward to seeing you in future videos. Thanks. Take care. Bye.